All right, hi everyone. Sorry, we'll get started. I left my iPad in lab, so I just had to run back and grab that real quick. So welcome. Only 2 more weeks. Great. Your last full week of classes next week, so that's very exciting. In terms of what's left for the semester, you have quiz 5 today if you haven't taken that yet. Nothing next week, and then quiz 6 when you only have 2 days of class. Next week will be the last review session normally on Wednesday. And then I can see if this room is available the Wednesday afterwards, like after classes ends, if we want to do an in-person review before the final, or I can push it to later in the week. And then I'll definitely have a Zoom session before finals. Is there any like preference for Zoom review or for in-person or Zoom review for the final? No? Okay. I'll see what just a room is available. I know it gets weird with like reading days and stuff. So if we do 2 Zoom reviews, that's fine as well. But there should be like a mock exam that comes out, I think if you fill out a survey, and then I'll put together some final reviews. Yeah.
Everything, or is it kind of like what's been focused on after exam 3 mostly, and then some of the rest?
It'll be pretty equal. Like I would say she said, I think in the group meet that it's gonna be about all equal. I would say if I had to guess, it'll be like 30 to 35% new stuff just because you haven't been tested on it yet. And then everything else will be split up between the other 3 exams. So I would say an even distribution. You have 2 hours to take the exam, and usually your in-person classes are 50 minutes. So think just like twice the questions because you have twice the time. So what is that, like 32? So 8 questions per chunk. Any other questions? Okay, cool. Any questions for me right now about content? Yeah. As in like the titration curves? Yep. So as in like acidic and basic, and then like strong acid, weak acid kind of stuff. Yeah, absolutely. So when we look at titrations, you're always going to have 2 components. Right, so that's your acid or base. Okay, for the most part, you are going to be doing a titration with 1 weak component and 1 strong component. Whatever your strong component will be, whether that's the strong acid or the strong base, this is what is being added to your weak component. So your weak component's usually in the beaker, right? That has the pH probe in it. This one is being pH'd. So you know the pH of the starting weak component, and then you're adding strong component into your weak component. I say this way just because I don't want to call it the acid or the base because it's not always a weak acid that's being titrated with a weak base or strong base, excuse me. All right, so if you have an example, you have a weak acid of HF, and then you're doing a strong base such as NaOH. So your weak acid is what you going to know the pH of, and the pH will change dependent on the NaOH being added to it. So if we have a weak acid and a strong base, where would that look like at the starting curve? This is your pH, and this is volume. Where are we going to start on our pH scale if we're doing a weak acid of HF with a strong base? Yeah, at the bottom, right? So if this is 0, this is 7, this is 14. All right, we're not going to start at 0 because we have a weak acid. It's not going to be 0, probably somewhere around 1 or 2, right? So something, right, maybe here. And if we're titrating with a strong base, so we're saying we're starting in acidic range. And if we have a strong base, does that mean that our equivalence point is going to be in the acidic or the basic range? It's going to be in the basic range. So your equivalence point is in your basic range. So whatever your weak component is, that's where you start off on your pH, but your strong component is where you end in your pH. If we're doing a titration of a strong acid and a strong base, right, whatever is just being, right, then the rules kind of go out of place. But whatever you know that's in your beaker, that's where you start, and then your equivalence point will always be 7 if it's strong and strong. So the anomalies here are when it's a 1 weak and 1 strong. All right, so do we see a strong spike at the beginning for a titration, or do we see kind of gradual? It's gradual, right? It'll change a little bit and then it'll kind of level out and then it will start to spike up before it finishes off that way. Okay, so I would say our equivalence point somewhere like here. Okay, what is this component or this part of the titration in blue? What do we call that region? That's your buffer region. Okay, and what do we use in our buffer region? What equation? We use the HH equation or the Henderson-Hasselbalch equation. So that's pH is equal to pKa plus the log of base over acid. Okay. You have to do some like limiting reactant kind of situations here when you're solving the Henderson-Hasselbalch equation to know how much base and how much acid is present. So that's a lot of math. At the equivalence point, what are we doing for pH? I guess during the buffer region, what does our typical equation look like for our ice table?
Subtract moles of like the base from the moles of the acid.
Yeah, so what's usually in excess during the buffer region? The acid in this case, right? So whatever your weak component is, in this case, the acid, that becomes your ice table. So here we have excess weak component. So that means that for our example, we have HF and water is going to F minus and H3O plus. So we're still in that acidic range and we're still forming those H plus ions. Okay, so we're using the weak acid and we have its conjugate base. So what happens at the equivalence point? Do we still have some of that weak acid component? Do we still have some of that HF? They're equal, right? So before the equivalence point, we use some of that strong base that's being added into solution to use up the HF, making more F minus. Okay? And that's therefore making more H3O plus. So in solution, once we get to that equivalence point, the number of moles of acid and the number of moles of base are equal. That means we know we use up all of the HF at the equivalence point. We use up all of the HF and form F minus. That F minus then reacts with the water in solution to form some of that HF again and H3O plus or OH minus this time. Now it's OH minus, right? We take the conjugate base of our weak acid that we were using previously and set up a new ice table. Right, and now we see we're forming that OH minus, which puts us in the basic range, right? We know that we're going to have a basic equivalence point because we're adding strong base, and because of that, and that is because at the equivalence point, the F minus that was being formed from using up the HF now has to reestablish equilibrium and form some OH minus. That's a great question. So if we have, let's say 1 molar HF and we have 1 molar NaOH, right? We can say that we added 10 milliliters of both. Okay, so if we added 10 milliliters of both, if we look, what are the moles then? If we added 1 mole, if you had 1 molar HF and 1 molar NaOH and we have 10 mils, it's 0.1, right? And we have 0.1 moles of both of them. So if we look at just like a general equation, right? We switch partners in this case where we form NaF and H2O. The NaF is ionic, so that will dissociate. So if we look at the net ionic equation, since HF is a weak acid, we're going to keep that together. So we have HF and OH minus form F minus and H2O plus, right? So a concentration of HF is 0.1 moles because we had 1 molar times 10 mils. Is that 10 mils? 1 times 0.01, 0.01. Yeah. I have 0.01 moles. And OH minus also is 0.01 moles. So our limiting reactant is both of them, right? We're going to use up both of them. What is our ratio of HF to F minus or a ratio of OH minus to HF? I'm sorry, to F minus. 1 to 1 to 1, right? So if we use up HF, how much F minus gets formed? 0.01. And if we use up all 0.01 molar OH minus, how much F minus gets formed? 0.01, right? It's the same for both of them. So these turn into this. So this is 0.01 moles of HF gets formed. In our ice tables, do we use moles or do we use molarity? We use molarity. So how do we get from moles to molarity? We have to divide by liters, and how many liters? So we added 10 mils of each of them. So what's our total volume? 0.02, right? Instead of having, we have 10 mils of HF and we have 10 mils of NaOH. So we have a total of 20 milliliters. So in order to get to molarity, we'll take 0.01 divided by 0.02, and we'll end up with 0.5 molar F minus. Okay. that then would be the starting point for your ice table here. Right, that becomes your initial concentration of your F minus. Does that make sense how that happens? Okay. Then you can do your normal ice table, right? You say you have F minus, you have 0.5 molar of that. You have the water that doesn't matter. And now you have no HF because we just used all of that HF to form the F minus, right? Yeah, and then you have no OH minus as well. So then you can just do your normal change and equilibrium. And then you will probably be provided the Ka for HF in this situation. So then you just take the Kb because now you're forming the base dissociation of F minus. Does that make sense for the equivalence point? Yes. All right, if we had a weak base, right, if we had NH3, what is the conjugate acid of NH3? NH4 plus. And what gets formed? OH minus. Yep. Right. NH3 is going to be, oh, that's a giant bug. NH3 is going to be a basic, a weak base. So it'll accept the proton from water, right, forming H4, NH4 plus, and then OH minus. So at the equivalence point, this is before equivalence point. At the equivalence point, it now will be NH4 plus and water turning into NH3 and H3O plus. All right, so that's what it looked like for a weak base. Questions at the equivalence point. Okay, then what happens after the equivalence point? What's in excess here? The weak or the strong component? The strong component. So after the equivalence point, we have excess strong component. So if you have excess strong component, what is a strong acid or a strong base going to do? Does it somewhat dissociate or completely dissociate? It completely dissociates. So it'll have enough concentration to use up any of the weak acid or base that's in solution, where it's not going to matter about that at all. So whatever is left over after it uses up all of those moles will turn just into NaOH dissociating. Okay, so whatever the number of moles and the total volume you have, right, will turn into the concentration of OH minus. And then you can just use POH directly there. Okay. So that would be this portion here after the equivalence point. Okay, does that make sense for the weak acid, strong base? Yes, okay. And then if we did the weak base, strong acid, your curve would just be inverted. It would have an initial pH of the basic region, so somewhere around 12, 13. And then your equivalence point would be in the acidic region because you're adding strong acid. Okay, and then you don't really need to do any calculations with it, but I think you just need to recognize it. So if you have something that is di or triprotic, then you will have two equivalence points in your titration curve. It'll look a little nicer than that. But if you see, right, two vertical lines, then how many protons does this acid have? It would be 2, right? So this is a diprotic acid. Right, something like H3PO4, right? Phosphoric acid. This would have 3 equivalence points. So you would see 3 vertical lines on your titration curve. Okay, does that help your question?
It's just how many vertical lines.
Yep, because each proton has a Ka. So each of those Kas would have an equivalence point. So depending on how many Kas there are, it should be how many vertical lines there are. Any other questions? Yeah. Mhm.
Looking at her quiz.
Mhm.
Can we just go over anything with you on the quiz?
Yeah.
pH at any point in strong acid base titration.
A strong acid base, yep. So let's look at HF, or sorry, HCl and NaOH. Okay, we're gonna form NaCl and all right, what do we care about in a strong acid, strong base? Right, if we're gonna write the net ionic equation for a strong acid and strong base, what actually is in that equation? Right, this just turns into H plus and OH minus goes to water, right? That's all that it is. So we're just looking at the acid, the H plus, the base, the OH minus, forming water. What happens? All right, so if we have
Strong acid, strong base always forms water and
a salt, yep. So any acid-base reaction will always form water and a salt. If it's a strong acid, strong base, it'll always be a neutral salt. If it is a weak and strong, then that's where we play the salts of, is this an acidic salt or is this a basic salt? And that's from whatever it came from on the other side. Someone give me your favorite number. 35. Let's do this question. You have 25 mils of 0.5 molar HCl and 35 milliliters of 0.25 molar NaOH. What is the pH of the solution? Anyone have any ideas how we're going to do this? Okay, right? We need to figure out what is our limiting reagent. And so in order to get to limiting reagent, we need to know how many moles of each of our component that we have. So we should have I think we have 0.0125 moles of HCl, and we have 0.00875 moles of NaOH. Do we agree there? All right, so what do we do with that? Which one is our limiting reagent here? NaOHs, right? So how much of our HCl are we going to use? Or how much of our NaOH are we going to use? We're going to use all of it. So then how does that play into how much HCl we're going to use? We subtract it, right? So for HCl, we have our starting, and we're going to subtract that from our base that we have. So we're left with 0.00375 moles of HCl. How does that help us with our finding the pH? Yeah, we can transfer it back to molarity. Once we know that all of our NaOH is added or is used up, we have no more of this, right? This goes away. So now all that's left in solution is HCl going to H plus and Cl minus. So we can use our concentration. What's our total volume now? 60, yep. How do we get to 60? So we added 25 milliliters and 35 milliliters. We have 0.0625 molar HCl. So what does that mean about H plus? It's the same, right? We know that our strong acid of HCl will dissociate into H plus and Cl minus. So what's left over is this going to H plus. So how do we get pH once we know the concentration of H plus? You just take the negative log. Perfect, right? So we're going to take pH is equal to the negative log of 0.0625. Then we end up with 1.20 as our pH. Okay, does that make sense? So you can do that for any point with a strong acid, strong base, whether that's at the initial and you just have an acid, or you're someplace where you have more base now that's in excess. You can solve that for anything. This is the same setup you're going to do for after your equivalence point as well, right? You're going to do the same, finding the limiting reagent. It should be your weak component. You should have excess, strong acid or strong base, depending on the titration. And then you just say, okay, what is that concentration? It dissociates it into either H plus or OH minus, take the negative log. Probably the most straightforward out of the 3 points on the titration curve. Okay, does that make sense for a strong acid and strong base? Okay, great. Do you want to do a practice of like a buffer region situation? Okay, so for this question, you have 100 milliliters of 0.1 molar NH3 being titrated with 0.2 molar HNO3. What is the pH when 10 milliliters of HNO3 has been added? And you're given the Kb of NH3 is 1.8 times 10 to the negative 5. Do you want to try this on our own and then we'll like reconvene a couple minutes? Yeah? Okay. Okay, so this should be where you started. Did anyone get a pH? (9.86), is that what you said? 8.6, okay.
I didn't do pH.
Okay, yep, you don't have to for this one, I don't think. And I might have plugged something into my calculator because I didn't write all my numbers down. So what did we do? So do we all understand why at equilibrium we have 0.008 and 0.002 moles of NH3 and NH4? Do we all know how we got there? Good, yes. How did we get there? Yeah. So from our question, right, we have 100 milliliters of 0.1 molar NH3, and that's being titrated with 0.2 molar HNO3. So what is the pH when 10 milliliters of HNO3 have been added to your solution? So what we're looking at is how many moles of each are we starting with? For our NH3, we have 100 milliliters at 0.1 molar. So if we do 0.1 times 0.1, then we get the 0.01 molar NH3 that we're starting with. For HNO3, and is NH3 a weak base or a strong base? That's a weak base. And then what about HNO3? What is that classified as? That's a strong acid, right? So we are starting with our weak component of the weak base, and we're adding strong acid to it. So when we add 10 milliliters of 0.02 molar HNO3, we're adding 0.002 moles of acid to our base. Which one is in excess, the weak base or the strong acid? The weak base is in excess. So all of our strong acid will be used up. How is that used up? We go to our ice table. In these situations, you can use moles for the ice table, but you have 0.01 moles that you're starting with, and you have none of your conjugate acid. The change is going to be the number of moles of acid that's added to your system. So that's the 0.002 moles. So we know that for every 1 mole of NH3 that we use, we're getting 1 mole of NH4 plus. So for every 0.002 moles of NH3 that gets used up, that forms 0.002. So at equilibrium, once all of your acid has been used, then we have 0.008 and 0.002 molar of the NH3 and NH4 plus respectively. Does that make sense? Great. Okay, so we're just looking at limiting reagent and how does that change in order to get to equilibrium. So once we are at equilibrium, what equation can we use? We can use the Henderson-Hasselbalch. What do we need to do first, though? We have to get the pKa, right? We have to switch our Kb to pKa. So we do that by doing Kw and Ka. So I got Ka is equal to 5.56 times 10 to the negative 10. Then we can plug this into our equation. So we have negative log of 5.56 times 10 to the negative 10 plus the log. Our base this time is in excess, so it would be 0.008 over 0.002. Okay, so I got pH equal to 9.86. Okay, yep. That's why I wanted to give you this one because you had to do a little bit of manipulation. Right, usually if it's a weak acid, then your base is on the right, that goes on top. But this time your base is the NH3. So you want to put that one on top because you still have excess of the base and then divide it by the acid. Yep. It would give you the same answer. You technically should be using concentrations. However, since it's total volume, if you divide by total volume on the top and the bottom, they will cancel out. So it would give you the same number. I don't think so. Unless they try to give you like in two separate equations, like if this were to combine with this, then what would it be? With no change in volume, but it would be weird to do that. I think most of the time you can just use the moles directly. Everything's going into one spot, so. Yep. Yeah, if you wanted to change this to molarity just to like use concentrations, it would be 110 milliliters, so 0.110. And you could check your answer that way too, by switching it to concentration. I just think that's 2 extra steps. It gives you the same answer anyways. Less room for error. Okay. And then always ask yourself at the end of the question, right? Does this make sense? Does a pH of 9.86 make sense for a weak-based titration? Yeah, it does, right? We still have excess base, we still have excess weak base, so we shouldn't be super close to 14 because it's not like super strong or anything. But we shouldn't be in our acidic range at least. So I would say that makes sense. You should feel confident with your answer. Questions? So, right, if you think about in solution, if you think about NH3 and HNO3 in solution, right? If I were to ask you to predict the products, what would you predict for your products? Right, you would predict NH4 plus and NO3 minus. I guess you have to switch your partners. This case, you're just taking your H here and putting it with this guy. So then we have to look at, right, what is being used. So when we're looking at what's being used, we have 0.01 moles of this and 0.02 moles of this. We said that the HNO3 is our limiting reagent because we have the least amount of moles. So when we have the least amount of moles, this goes away. But what does that turn into? That turns into some of your products here. The NO3 minus is a spectator ion, right? Because if we were to write this out, it would be NH3 plus H plus NO3 minus, forming NH4 plus and NO3 minus. So this would cancel out. So what we really care about is how does NH3 plus H plus react to form NH4 plus. So now if we look at the moles here, we have 0.001, I'm sorry, 0.1 and 0.002. What does that form? The product of NH4 plus. So you kind of do an ice table without it actually looking like an ice table. If you do it this way, because you're doing the change to see how much product is being formed. You don't have to use the ice table if you can just do it this way. The ice table is just there for a tool and in terms of like keeping your thoughts organized. Like if it were a strong acid and strong base, right? Like, so if it's not if it's not a buffer, then it's probably a strong acid, strong base, or it's a weak acid and a weak base, and that's just, we don't really care about that, in terms of like the scope of this class. Mhm.
Don't, then you.
Yes, yep. Always, I think the first thing you should always do with these types of questions is just identify what your acid and base are. Are you working with two strong things? Or are you working with a weak and a strong? Because if you get your head straight there on what do I have, then you can say, okay, if I have a weak and a strong, I'm doing buffer stuff. If I'm doing strong and strong, I can just directly go to things dissociating. Does that help? Right, and if you think about, right, using up the HNO3, now you're just left with NH3 in solution. So then it's like, okay, what would NH3 in solution do? And then that forms the ice table. All right, just think about NH3 floating around in water, and I'm like, what's going to happen, right? What chemistry happens? And hopefully that paints a picture for you. Okay, any other questions on that one? Do you want to do one at the equivalence point? Keep in mind, I've been showing you things that are 1-to-1 ratios. At any point, right, if this is a diprotic acid or base, then you would have something that is 1-to-2. So think this guy here. Just remember, we are always like skipping a step saying this is a 1-to-1 ratio. If it's a 1-to-2, you know that you have 0.1 moles of this and you have 0.2 moles of this. So if you have 0.1 mole of NaOH, you can always use your coefficients of your equation. And so you would say that you need 0.05 moles, right, of that to be used up. Okay, so just make sure that we're always doing that step. We are always doing that step, but we always recognize it as 1-to-1, so we don't really show it. But just remember, your coefficients matter in these types of problems as well. All right, so we have 0.5 molar NaOH is added to 0.25 liters of 0.25 molar HF. How many milliliters is required to get to the equivalence point, and what is the pH of the equivalence point? Okay, so for the sake of time, I'll run you through how you would do this one. So we have what first? What is NaOH? Strong base. And what is HF? That is a weak acid. Yep. So we have HF and NaOH forming NaF and H2O. All right, what we care about is the air, I guess, do we have a buffer? Like, yes, and we did. Right now it's iffy. So our buffer of HF would be F minus and H3O plus. Okay. So in order to determine how many milliliters are required to get to the equivalence point, we're just looking at moles being equal. If moles are equal, then we can use M1V1 is equal to M2V2, or the moles of acid times the volume of acid is equal to the moles of the base times the volume of the base. So what that looks like is right, 0.25 molarity times 0.25 liters is equal to 0.5 molar concentration of your base. So we should end up with 0.125 liters, which is 125 milliliters of NaOH that have to be added. Okay, questions on the first part of that one? Alrighty. So then the second question is, what is the pH of the equivalence point? So we know that the pH, the moles are equal. So what is our limiting reagent at equivalence point? Both, right? They're both going to be limiting, they're both going to be totally used up. So if that is totally used up, then we have 0.0625 moles here and 0.0625 moles here. All of those 0.0625 moles turn into the moles of 0.0625 NaF, technically. NaF is going to be an ionic salt, and that will dissociate completely. So now we're thinking, okay, in solution, I just have Na plus ions, I just have F minus ions, and I have water molecules. The Na plus is not going to do anything, that stays soluble. The F minus, though, is the conjugate base of a weak acid. Oops. Right, is the conjugate base of this F minus. So what happens there? Now in solution, F minus and H2O goes to HF and H3O plus. We have 0.0625 moles of this. And we have a total volume of 375 milliliters or 0.375 liters. We have a total concentration of 0.167 molarity of our F minus ion. This now becomes the starting point for your ice table. Because what is the F minus ion going to do in solution? It'll bounce around and interact with the H2O. We used up all of our HF in solution, so we have none of that. So now we have minus X plus X and plus X. So 0.167 X and X And then that just turns into, sorry, this is not usually plus. Minus. Now that turns into KB is equal to x squared over 0.167. You would be able to use the assumption there. And then you would be given a KA probably 1.8 times 10 to the negative 1. Right, so then you can do the same thing that we did for NH3 to solve there. Then it just becomes a typical weak acid, weak base situation. I don't know what that answer is, but you can solve for it. Okay, so then we would get, this would turn into X is equal to the concentration of OH minus, so then we go to POH for negative log, and then 14 minus POH. We give you the pH. So that's how you finish out that question. Okay, questions there? That make a little bit of sense on what's going on? Alrighty. Well, it is 6:02, so I will let y'all go. Sorry for starting a little bit late today. Yeah, if there's any questions, please feel free to come ask me. And then good luck on your quiz if you haven't taken it yet. Just make sure you start it before like 11 at least. And I will see you and have a great no class on Friday. And I'll see y'all next week.